So chapter 3 is an idea of understanding what polynomial functions are all about. So when we talk about chapter 3, what we're talking about is all sorts of things dealing with polynomial functions. So this includes linear functions, but for the most part we're going to be talking about things that are a higher degree than just linear ones. And the first one above a linear function is a quadratic function. And that's what section 1 is going to talk about in chapter 3, is a quadratic function. So what we need to know is what exactly a quadratic function looks like. And the most basic quadratic function is this. That is a quadratic function model. Okay, and A, B, and C are just any number that you can pick out of any, pick at random. And what we need to talk about are specifically how you graph things today and specific properties of these graphs. So what we're going to talk about is how you compare graphs and what the differences are between them. So what we're talking about first of all is how you sketch a graph of a quadratic function. Now it's going to start to look a little bit a little messy with all these graphs, so I'm going to try and graph these all on the same one. So if you have questions about them, please ask, or if you want to just make another graph, just do that off to the side. So compare these graphs. Well, I'm going to draw the very most basic quadratic model. And if you square something, you get 0 when it's 0, 1 when it's 1, 4 when it's 2, and 9 when x is 3. So here are my points. So here's the first part of this graph. And a quadratic graph is symmetrical. So if I were to pick -1, -2, and -3, I would get 1, 4, and 9 as well. So it would look something like this. So here is my curve that talks, or that shows what a quadratic looks like in the most basic sense. Now if we're going to compare this with 1/3 x squared, then we need to describe what's going to happen to it if we do this. So I'm going to make another column for part A. And we're going to talk about this new function, which says I want to take and multiply this parabola by 1/3. So when x is 0, it's still going to be 0. So that point is still there. When x is 1, we're timesing it by 1/3. This new point is 1/3. So I'm going to put a dot right there. Properties of symmetry say the other one is 1/3 as well. So that's over there. When x is 2, y is going to be 4. But when we times it by 1/3, it's going to be 4/3. So I'm going to go to 4/3, which is about right here. Then for 3, it's going to be 9 in the original graph. I'm going to times it by 1/3, I get 3. Oh, that's 2. And so these are all symmetrical, so I'm going to put these on the other side as well. And I'm going to draw this curve as well. So you can see here, this curve is not as steep as the other one. So this 1/3 here makes this a vertical shrink of the original one. Okay, so it makes it a little smaller from a vertical standpoint. Now what I'm going to look at is how taking a number other than a fraction deals with this, and that's letter B. So we have this 2x squared. So when it's 0, the original one was 0. We times it by 2, it's still going to be 0. When it was 1, it reduced to 1, or it equaled 1. So when I multiply it by 2, I get 2. So that's actually going to go right here. Properties of symmetry say it's the same. When it's 2, the original parabola was 4. So now it's going to be 8. So it's all the way up here. And when it's 3, it's all the way to 9. So if we times that, we get 18. So that's way off the graph up here on both sides. So in terms of a graph, it's hard to make this curve and compare them both, but the curve is a lot more steep than the original one. So this is a vertical stretch of the original graph. So all we've done is just shown what the graph looks like and how putting a number in front of it changes the physical appearance of the graph itself. And it changes it from a vertical standpoint by making it more steep or less steep. So the same types of things you're going to see here. We're magnifying this by 1/2. So in terms of a graph, if this was my original one, we're going to multiply all the y's by 1/2, so we're going to shrink this one by 1/2. So each one's going to be 1/2 less than the original one. So it's going to be a little bit smaller in terms of this. And now I'm not going to draw a ordered pair graph for all of them, but if you want to see it, let me know and I can show you how I get to this point. And my graphs aren't perfect, but if you want, I can certainly show you what it looks like on a graphing calculator in class. Now this one's a little bit different. We have this number in front, but it's negative. Now when we talked about what graphs of certain functions look like, this negative meant something. This negative meant a reflection. So we're going to make it smaller from a vertical standpoint, and we're also going to reflect it. So instead of this parabola looking up like a U, it's going to look down, but again, it's going to be smaller from a vertical standpoint. Okay, these aren't perfect graphs, but if you want, it's going to be a lot smaller, and it's going to be a reflection. The same thing here. This is a reflection, but it's going to be a lot steeper than the original one. So this one's going to be a reflection as well, and it's going to be a lot steeper. So it's going to be a lot more of a severe curve from a vertical standpoint. Now again, I'm not drawing these perfectly, and I'm not drawing ordered pairs either. But what you need to know is the effect that it has on this. Now this last one has a 3/2 in front of it. So we're not reflecting it, but we're making it bigger. So we're actually stretching this graph out by a factor of 3/2. So it's going to be a little bit more steep than the original. Okay, so that's what all these graphs look like. So this is C, here's B, this original one is A here, and here's D. Now this is a mess of all these graphs, but you need to know what these numbers have on the effect of this. So the number in front of the x squared. So the number in front of the x squared has an effect on vertically stretching or shrinking the graph and reflecting it. Okay. Now, when we talk about specifically how you graph things, you're going to see that there's another way to graph these, and it's a whole lot easier because the only way that we know how to deal with right now is if you have a bunch of ordered pairs and graph them. And you saw I was doing a freehand sketch of all of that, and it didn't work out the best. Okay, so I'm not the best drawer of those, and I'm not expecting you all to be experts at it as well. So we have to find a better way to do this. And the way to graph these, there is a specific way. It's called standard or vertex form, so that we don't need to plug points in. And this is what it looks like. Okay? Now, you might say that's a lot of notation. What does it all mean? Well, there's a couple of things that you need to know. That there is a vertex of this graph. The vertex is basically what the point of starting of reflection is on the graph. And for this, the vertex is going to be at the point h, comma, k. Okay? And another thing you need to know is that with all parabolas, they're going to have what's called a symmetric axis. And this axis is going to be at the point, or the line, x equals h. So everything's going to be reflected across that axis. Now, we need to talk about how you do this. And I need to resort to how we did something way back when. So I'm going to kind of scroll down and ask that you recall something. And it was this process called completing the square. So if we have something, doesn't matter what it is, what number makes this a perfect square? And the way we did this, we took half of this, then we squared it. Okay, so we took half of that and then squared it. So half of 4, and then square that to get a positive 4. So that makes that a perfect square. And the way that you factor this then is whatever number you got after you halved the number in front of the coefficient of the x term, that was the second part of your complete square. Okay, you might ask, how does this apply to some other ones? Well, let's take a look at something else. Let's just say we have this problem here. And we had a problem like this in previous sections, and it asks us to complete this square. Okay? So we don't want a number in front of this term here. So I'm going to divide everything by 3. So I get rid of that. Well, actually, we'll do that right now. So if this was equal to 0, we'll divide everything by 3. So we have x squared plus 5/3 x plus 7/3. Then we usually moved this to the other side. So we made it a negative 7/3. Then we took half of this, so 5/3 times a half, to get 5/6, and then square it to get 25/36. So then this was 25/36 that we added to both of these. And then from here, whatever my term was that I got after I took a half of it, in this case 5/6, was the way that this factored. Now I'm not completely solving this, I'm just recalling the process for you. Okay? And whatever this was, we got some number and then we took a square root. Now, this process is going to come in handy when we talk about how you solve something like this. And I'm going to show you how it's dealt with. And there's a few little algebra properties that we need to be aware of in order to do this. But we're going to complete the square so that we have a parabola that's very easy to graph.